So I'm Pedro Monajo, and I'm happy to present our paper on dropping standardized testing for admissions, which is joint work with Nikhil Garg and Hanali. So the use of standardized testing in admissions is a very timely question. So for example, we recently saw University of California who decided to permanently drop the testing requirement for its applicants, and also announced that it has plans to design its own test. And independently of this decision, and because of the COVID-19 pandemic, we saw some other colleges that started dropping this testing requirement, potentially temporarily or more permanently. So the use of standardized testing in admissions is an open and difficult debate, and it centers around two main arguments. So informativeness and disparate access. And on the one hand, we have test supporters who say that test scores offer a systematic way to collect information about applicants, and that other application features like essays or recommendation letters can be more unreliable than test scores. And on the other hand, we know that test scores have racial and socioeconomic gaps, and that certain groups of students may face access barriers to testing. So for example, we have this study from 2016 that found that for every 10 poor students who score college ready on this test scores, there are 5 other poor students who would score college ready, but who actually take none of these exams. And so motivated by these two competing claims, in this paper, we developed a Bayesian framework of statistical discrimination to study the following question. So what would be the effects of dropping the testing requirement on metrics like academic merit, diversity, and individual fairness in college admissions? And our main takeaways is that test scores and other features variance, so their informativeness really matters and can have an ambiguous impact on disparities. And this holds even in the absence of prejudice. And we also find that the interaction between information and access is actually complex. So on the one hand, dropping test scores may sometimes lead to a less diverse, less academically qualified class. But on the other hand, we show that when there exists substantial barriers to testing, dropping test scores can actually improve both academic merit and diversity. So we studied this question using theory simulations and a data application with data from the Texas Higher Education Opportunity Project. So let's jump right into the model. So in our model, there is a single selective school with capacity C that receives applications from a continuum of students. And we will assume that this continuum of students has mass normalized to 1. And the students belong to one of two groups, A or B. So in our model, every student is characterized by a true skill variable, a latent variable, that we call Q, and is drawn from a normal distribution with parameters mu and sigma. And what's important here is that both groups, both A and B, actually have exactly the same skill distribution. So we can say that both groups are equally skilled. And the problem here is that the school cannot really observe this skill level, but instead they see some noisy features. So we can think about these noisy features like the different application components, like test scores or high school grades and so on. And each such feature is the sum of the true skill level Q plus some Gaussian noise, independent noise. And the parameters of this noise distribution can differ, first across different groups, but also across different features. And we also have the school in this model who observes the information about the student, their group, and also their different features, or some of their feature or all of their features, and use this information to estimate the student skill. And then the school, who cares about merit, so this is the optimization objective of the school, admits the top massy of students with the highest skill estimates. In this paper, of course, like to evaluate the different policies we will see, we need to define some metrics. And specifically, we have 3 metrics here. So we use academic merit, which is the expected skill of admitted students. And we also have diversity level, which is the fraction of group B students, or what we will call the minority students in the admitted class. And finally, we have what we call the individual fairness gap, which is the difference in admission probability between 2 students who have the same true skill, but just belong to different groups. Okay, so next we will talk first about the Bayesian estimation process of the school in a greater detail and some simple intuition about the model. And then we will specifically talk about policy design. So we will look at test-based policies, but also test-free policies with and without barriers. Okay, so let's now look again at the Bayesian estimation procedure of the school. So as we said, the school will observe the group and some features of an applicant and compute their perceived skill estimate. And the school will repeat this process for every single applicant, right? So at an aggregate level per group, the school will get what we call a perceived skill distribution. And as we see on the right box here, in the form of this perceived skill level distribution, the variance of this distribution depends on the sum of precisions of the features of the group. And naturally, one of the 2 groups, and we can assume that this is group A, has a higher total precision in their features. So we can now think about what this basic difference actually means. So it means that even though we start from identical true skill distributions and the school is Bayesian, this assumption we made on the differential informativeness will lead to a higher variance in the perceived skill level distribution of group A. So essentially the intuition is that because of the higher uncertainty in the features of group B students, their estimates at an aggregate level are more conservative, which means that this perceived skill level distribution for group B is more concentrated around the mid. So this already tells us 2 things. So first of all, the school can successfully eliminate bias. So we see that both distributions have the same correct mean, but the school cannot really correct for variance. So there is a limit there. Right, so even though the school knows that the two groups must have the same variance, it fails to correct for them. So what does this mean in practice? So in practice, a selective school will come and will set an admissions threshold like we see here. And we will see that more students from group A will be perceived to be high skilled compared to the threshold. And as a result, more of those students will be admitted to the school. So in the end, group A students are admitted at a higher rate than group B students, which naturally means that group B is underrepresented at the school. And I just want to mention that this is a point where the assumption that C is smaller than 1/2 is important, because this means that the threshold lies at the right tail of this distribution. Okay, so our first theorem essentially utilizes the intuition I have just explained. So we already talked about the diversity level. In terms of the individual fairness gap, we find that very high skilled students in group B have lower admission probability than same skilled students in A. And in terms of merit, we find that not only group B students are underrepresented, but essentially the targeting of the high skilled students in that group is worse. So now we can also look at what happens when we drop test scores. So in this case, like dropping a test score in our model means just dropping a feature, right? Which is the test score. So in this case, we find that diversity level might decrease. The individual fairness gap will increase for high skilled students, but it may decrease otherwise. So for these 2 results, the direction of the result depends on the informational environment, so the variances of all features. And finally, for academic merit, we find that it decreases for both groups, which is expected because essentially we lose some source of information with the test. So the previous result essentially assumed that all students had access to the test. So now a natural follow-up question is, okay, what happens if only a fraction of each group, a fraction gamma g of each group has access to the test? And without a test, then students cannot apply to a school that requires it, even if they are qualified otherwise. So in this case, we have a threshold characterization result. So we show that academic merit of group G improves after dropping test scores, if and only if this group faces barriers below that threshold that we find. And observe that this threshold actually depends on all the moderate parameters. So essentially, there is a nice trade-off here that the graph on the left essentially explains. So there are two competing effects here, right? So on the one hand, dropping test scores increases the applicant's pool size, which is good, okay? But on the other hand, the composition of this applicant pool also matters, and the information loss that happens when we drop test scores is not necessarily beneficial for the minority group. So now we can actually test the theoretical intuition with data. So here is the data we have from UT Austin. So we have several features: high school rank, standardized test scores, demographic features, high school features, admissions and enrollment decisions, and finally transcript data like GPA. And the major challenge we have here is that we actually need outcome data for both those students accepted and enrolled and those who were not accepted or did not enroll. And this is data we don't have, and in general, it would be very hard to get. So to overcome this challenge, we essentially consider our applicant population to be all the enrolled students, all the freshman students, and we simulate a setting where students need to be selected for an honors program or a college transfer, something like that. And we also need an outcome variable. Okay, so we thought that GPA could be a reasonable proxy for what we call true skill in our model. And finally, we use other features like high school rank, standardized test scores, and major as additional features. And finally, we also use the high school's relative economic privilege index to define the two groups of students, so the privileged and disadvantaged students. And with all this data, we train two models using OLS, and we sample an equal number of each of these groups. And we also assume, and this is an assumption, that 2/3 of the disadvantaged group have access to the test. So here are our results very briefly. So in the low informativeness case, we find that dropping test scores actually decreases diversity and academic merit. And this is because the high school rank, which is essentially like one of the major features that remains, is very uninformative for the disadvantaged group compared to test scores. But now if we consider a high informativeness case, so essentially, if we now add the first year GPA as a feature, and we exclude this from the final GPA, right, the outcome variable, then we see that dropping test scores increases both academic merit and diversity. Okay, so I don't feel like I have time to go in detail over the related literature, but I just want to mention that this work contributes to a long line of literature in economics and fair machine learning. And finally, to conclude, I would like to reiterate the main message of our paper. So we show that test scores and other features variance really matters and has an ambiguous impact on disparities. And we also saw that the interaction between informativeness and access is complex. So actually dropping test scores may sometimes lead to a less diverse, less academically qualified class, as we showed. But when there are substantial barriers to testing, then dropping test scores can improve both academic merit and diversity. Thank you.
Alrighty, any question? Yeah, can you also say what happens with strategic behavior in terms of who opts to give tests?
Okay, I think this is a very nice question. We don't really look at this question in this paper because we assume that the two options we consider here are the either like to drop the test or not consider it at all at admissions or keep the test. But there's this nice question in the middle, right? What happens when we have optional testing policies so students can decide whether to submit the test or not? And I think the next talk actually will talk about this.